some application type of problem. So our first example is air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. Sorry, it's so tiny. You'll make do. So the first thing I want you to look at is the information that's being given. Right here, 5 centimeters cubed per minute. Is that a rate? And that is a rate of change of what with respect to time? Volume. So what they have given us here, and our best way to write it, in my opinion, is the derivative of volume with respect to time, dV dt, is equal to 5 centimeters cubed per minute. In all of these problems, let the units help you figure out what they are trying to tell you. Okay? So that's the rate of change of volume with respect to time. Determine the rate at which the radius of the balloon is increasing. So, rate at which the radius of the balloon is increasing. If I wrote the derivative of volume with respect to time as dV dt, then what am I looking for here? The rate at which the radius of the balloon is increasing. dr dt is what we're looking for. Good. When the balloon, when the diameter of the balloon is 20 centimeters. Diameter equals 20 centimeters. Okay. So I've written down everything I know, and I've written down what I'm looking for. And when I say I've written down everything I know, I've written down everything they have told me. I am dealing with a sphere, and I am dealing with volume. So what is the volume of a sphere? On the board. 4/3 pi r cubed. Good. So if I can take the derivative of this function, then I have some information I can use. dV dt is 5. Diameter is 20, so of course that means our radius is 10 centimeters. And we need to find dr dt. All right, so we're going to take the derivative of this volume function. So you can consider this your primary equation for this type of problem. And when we do that, we get dV dt equals, what can I do with the 4/3 pi? Just leave it out there, 4/3 pi, times the derivative of r cubed with respect to time. 3 r squared, thank you, dr dt. Implicit, we're taking the derivative with respect to time, so we need chain rule or implicit differentiation there. And now we have an equation where we know dV dt, we know r, we can solve for dr dt. Do that now, please. Why is it what? Perfect. Okay. It does, 405. We've got 4 times 5 times 100. Our radius squared. 10 squared. And you will always need units. Again, the RDT is the change in radius with respect to time. Radius is measured in what? Centimeters per minute in this case. for our rate. And there's our solution. Questions on what we do? We are going to get 3 examples of the class 6 pipe. So we have this volume of a sphere. We'll look at a triangle and we will look at a cone. The cone comes up quite often. So any questions on what we did on this? Oh, because it's got an interesting characteristic. It's kind of fun to work with. All right, so our next one. A 15-foot ladder is resting against the wall. The bottom is initially 10 feet away from the wall and is being pushed towards the wall at a rate of 1/4 feet per second. How fast is the top of the ladder moving up the wall 12 seconds after we start pushing? There's a lot going on. So, just like with all of our application problems, we can draw pictures to help us, and I always do. And we'll write down what we know and what we are looking for. Oh boy. There we go. That's my ladder. It's a little bumpy. All right. So my ladder is here. And how long is the ladder? 15 feet. And I'm going to call that C, A, B, and C for this right triangle. All right? And the bottom is initially 10 feet away from the wall. So it initially looks like this. Okay. What else do I know?
The rate.
I know the rate for what?
So decrease to B.
So, good. So we'll call this B, and we'll call this A. And if they say that the bottom is initially 10 feet away, and it's being pushed towards the wall at a rate of 1/4 feet per second, what have they given me with respect to my variables A, B, and C? B, 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 C. And is my length getting bigger or smaller? Smaller. So my rate should be negative. Okay, feet per second. Good. And we want to know how fast is the top of the ladder moving up the wall 12 seconds after we start pushing. So T equals 12. And what is it that I'm trying to find? The ADT is what I'm trying to find. So our first task is to find a relationship between our variables. So what do you think we'll be using? We'll be using Pythagorean theorem. So we have a squared plus b squared equals c squared. Okay? And we are looking for the ADT. So we will be taking the derivative of this equation. And what will we get? 2a the ADT. How do we get that? How do we take the derivative x plus y equals 12 when we do it implicitly? We get 1 plus 1 dy dx, right? Equals 0. We're doing the same thing, but with respect to time. Okay. All right. So we have 2a dAdc plus 2b dB dt equals 2c dc dt. Given these problems, you always want to look for any rate or any variable that is not changing, because the rate will then be what? If the variable is not changing, if the variable is staying constant, the derivative of a constant, or the rate of change of a constant, is 0, which makes our life much easier in dealing with some of these equations. So our side C is the ladder, and that length is not changing. So that means that dc dt equals what? Equals 0, which makes it very nice down here. this ends up being 0. All right, do we have everything we need to find what we're looking for? Here, you with me? There you go. Okay, just checking. All right. Do we have everything we need? What am I missing? I'm missing A, and we need to remember that we're not doing this at the time that this triangle is drawn. We're doing it 12 seconds later, correct? So really, is my B length 10? No. So let's figure out what my B length is. How would I find that? 12 times the rate. So our distance for B is going to be rate times time. And what's the rate? 1/4 times the time, which is 12. So it has moved 3 feet. So my B is not 3, my B is what? My B is going to be 7. And do that. So we show that we shorten this up. So our B is 7. So now, back here, I'm going to need A. I'm looking for the ABT. I'm going to need B, and I have the BBT. So how am I going to get my A? Pythagorean theorem at this point in time. So we are going to do A squared plus 7 squared equals 15 squared. Solve that for me, please, and give me a decimal. That would be fine.
13.27.
What is it?
13.2664.
13.266,
665.
we'll say. Okay. All right. So our A is 13.266. All right. Now we have enough information to solve for the missing parts. Plug in all of our parts and solve for the ABT. Do this at your desk, please. When doing related rate problems, our physics and vector conventions hold. So up is usually considered positive, down is considered negative, increasing is positive, decreasing is negative. You need to look at the length of what is going on to figure out whether your rate is decreasing or increasing. So go ahead and find our DABT. So we end up with the ABT equal to 0.132 feet per second. The way it worked out in our problem, it came out to be positive. Does that make sense? Because the ladder is going up the wall. Yeah. All right. That is it. Questions on that one?
Is that a negative 1.6?
Right here it is.
How about that 11?
I made it a positive because I add that to the other side to solve. Yeah? Daniel?
How do you, like right at the top, how do you get ECEC? Like, how do you figure out it's 0?
Because this length, as we push this ladder in, side B is changing, right? And the top of the ladder goes up, so side A is changing. But the ladder length is not changing.
Oh.
So the ladder is a constant length, so its rate of change would be 0. Okay. So you always want to look for that, because it makes life easier. If there is one that you can find that will have a rate of 0. Anything else on this one? Okay, one more, and then you get work time and practice time. All right. It's a favorite. So here we have a tank of water in the shape of a cone is leaking water at a constant rate of 2 feet cubed per hour. What did they just give me? Rate of volume. So they gave me dV/dt. And what does that equal? Thank you for the negative. That's really what I'm looking for. -2 feet cubed per hour.
Do people actually measure stuff in feet cubed per hour?
They do in calculus. If it were a drip, I hope not.
Yeah.
Okay, so the base of the radius of the tank, remember the base is actually up here at the top in this drawing, is 5 feet, the base radius, and the height of the tank is 14 feet. All right, which they have labeled on our picture, 14 and 5. Now, big stars, when dealing with our cone problem, we need to remember our most useful piece of information is the proportion of radius to height is consistent all the way through the cone. The ratio of radius to height will stay the same all the way through. So, this little equation that we're writing right here, what is the radius? 5. What is the height? 14. Becomes very useful in getting our volume into one variable. All right. So, part A says, at what rate is the depth of the water in the tank changing? What am I looking for? The HDT, because they have the depth measured as H. So we are looking for the HDT. Okay? When the depth of the water is 6 feet. So our H is 6 feet. Okay? All right, volume of cone. Kristen?
No, I don't.
Oh, okay, go ahead, you can ask the question.
But on our test, do we have to know, like, volume?
All right, it's a good question. Generally on, I follow the AP conventions. Generally on the AP test, they give things like volume of a sphere, or volume of a cone, or surface area of almost any odd shape, you know. They don't give area of a circle, they don't give circumference of a circle. They don't give the basics, but if it's one of these ones that if you don't see it often enough, you will forget it. They generally give what you know, okay? So I will follow the same information. Okay, moving on. So now, back to volume of a cone. It is 1/3 pi r squared something. H. All right. So now you see we have two variables, yes? So if I were to take the derivative of this equation right now, tell me what I would need to do. Sure, leave that out in front. Then what? Product rule. I would use product rule, and I would get a dRdt, and I would get a dHdt. Yes? You can do it that way. I find it more error prone. So let's get this in terms of one variable. We have r over h equals 5/14. Well, that means that r equals 5/14 times what? Times h, yes? All right. So let's get rid of r and find the HDT, since that's the variable we want anyway. This is 1/3 pi times 5/14 h squared times h. I'm waiting. Everybody okay with that? Yep. Now let's simplify it and then take the derivative. So we get b equals, I see 25 over 196, so I have 1 pi over 3 times 25 over 96 h cubed. Do you agree? Okay. Take the derivative. And don't forget your DHBC. The derivative of h cubed. All right, do we have everything we need? We have the BBC. That was given. Do we have h at the time we're interested? Yep, that's 6. And we're looking for the HCC. So, pencil to the paper, get your calculators out, find it for me, please.
So h equals what?
6. They told us for this point in time. And give me a value when you got it. Go big, go big.
Negative 0.139.
Negative 0.139. Negative 0.139 is what we've got. And you got that with 2?
3 times 6 squared. Oh, God.
Did I lose a 3? From what I put up here? I don't think so.
Well, it should be 3h squared dht, right?
3h squared, yeah. The negative 0.139 is correct. I just want to make sure I got what I have up here is correct. Negative 2 times 196, divided by pi, divided by 25, divided by 36. Yes, that is given up above. They gave us that the volume was leaking or changing, decreasing by 2.
25 goes to the bottom.
Well, when you multiply by the reciprocal, right? Divide by a fraction, multiply by the reciprocal.
So I'm like,
What if
because I have negative 2 times 196.
per hour?
And then the bottom multiplied out from that 5.
Oh.
And then I did negative 2 times 196 divided by 900 pi, so I negative
The 900 pi, I don't have
And we can go for like 8 hours straight.
So divide by Other questions here? Yes, quietly? Yes.
So when you're taking the,
Hush, hush, so I can hear the question.
so when you're taking the derivative of volume, why is it dVdt instead of dVdt? Like this, right?
Because we want rates with respect to time. Right? We want all of our rates, even though there's R's and H's in there, we want all of our information is given centimeters cubed per minute, feet per hour. So our rate has to be taken with respect to time to get the proper units in the end. You could certainly take the derivative of V with respect to H. But then when you take the derivative of R, you would get the RDH. Do we have that anywhere? The derivative of R, that information? The rate of change of radius with respect to height, we do. So that's why we have to do it with respect to time. Okay. Anything else on this one? Okay, we have a second part. And the second part says, at what rate is the radius of the top of the water in the tank changing when the depth is 6 feet. So what am I looking for in part B? I'm looking for DRDT. And the proximity of my work for letter B here is very nice because I have an equation for R right here, right? That's the easiest place to get DRDT. So R equals 5/14H. So DRDT will equal 5/14 times what? The HCT. And we just found the HCT in the previous problem, did we not? So it is 5/14 times negative 0.139. So we will get the RDT equals, what is that? My calculator friends. 0.049. And should it be positive or negative? It should be negative. The radius is getting smaller. And it would be what unit? Feet per hour, I think, in this one. Oh, that's strange. There it is. All right, so there is our part B. Okay? So, the more organized you can be on these types of problems, so you can go back and find relationships like this that make the part B very easy, the better off you will be. Questions on the process? Okay. All right. So, now I have a work problem for you.